So like I was saying before, make sure you have your work in front of you so you can actually see what you did wrong and see where you missed the points. So I'm going to go through each of the parts. I can find my pen. There it is. Okay, so after I finish going over the Q1, I will kind of talk about some of the things I learned last night, and then what we're going to do next week. So we're going to do some more FRQ practice next week, but we're also going to do something with the AP classroom. So like I said before, if you just came in, make sure you have your work in front of you for Q1. All right, so let's look at the first question. So the first one, we have a redox reaction, and the first question is asking you whether it's acid-base, whether it's reduction-oxidation, or gravimetric analysis. Okay, first of all, you can eliminate gravimetric analysis right away, because if you go and look at the data that they collected, or if you look, it says it's a titration. Titration is not gravimetric analysis. Gravimetric analysis is where you collect a solid. So you're doing something in which you have to collect a solid. Titrations, that would be volumetric analysis, where you are reacting a liquid with a liquid or a solution with a solution. So it can't be gravimetric. So you're either looking at an acid-base or you're looking at reduction-oxidation. So if you want to know if it's oxidation-reduction or redox, all you have to do is just see if any of the oxidation numbers change. So if you look at Mn right here versus here, well, chlorine is a -1, so that means that this has to be a +2. If it's in permanganate, it's going to be a +7. So the oxidation number here has changed, so it has to be redox. Like, you don't even need to go through and check all the oxidation states just to do that particular piece. Because if any of the oxidation numbers change, then that means if something is oxidized, something is reduced at the same time. That's the way it has to work. So we know it's going to be reduction-oxidation titration, just on the fact that the oxidation numbers change. And all you have to do is say it's redox because the oxidation number here changed from this to this. And that's all you have to say for that. So the next part of the question is asking about writing the net ionic equation. Okay, so there's two ways to do this. There's the long way, and if and only if they give you a fully balanced reaction, there's a shortcut. So I'm going to show you the method that you have to employ if they do not give you a fully balanced equation. So like if there were no coefficients here, or if they only gave you the sum of the equation, you would have to use the half reaction method. So you have to write the reduction reaction, you have to write the oxidation, and then balance it from there. So the first thing you're going to do is you're going to want to see, okay, what's being oxidized, what's being reduced. This is 7, and this was +2. Okay, so any of the group 1s, as long as it's an ion, it's going to stay a +1. So as long as you don't have like sodium as a solid or potassium as a solid anywhere in the reaction, it's going to stay a +1. So that means it's a spectator. It's going to end up being pulled out. Now the chlorine, if you see, you've got a chlorine here and here, and they're different polyatomics. The oxidation number has to change if that's the case. So oxygen is going to be -2, and remember this is an ion. So ClO3 has a -1 charge. So oxygen has to be -2. There's 3 of those, that's a -6. So this has to be a +5. So then if I come over here, so ClO4 has a -1 charge. Oxygen has to be a -2. There are 4 of those, so it's -8. This has to be a +7. So there's where our change is. This is being reduced, this is being oxidized. So you're going to write out, you have this. You do not leave off the oxygen because it's part of a polyatomic. If it's a polyatomic, you don't separate it. This The potassium is a +1 here, it's +1 here. I don't care about it. Then I go to this. This is an ionic compound. The Cl will be separated if it's in a solution. So then I just have the Mn. That's the difference between this and this. This is part of a polyatomic. The Mn is part of a polyatomic, so it has to stay together. This is part of an ionic compound, so I can get rid of the Cl. All right, so this is my first half reaction. Now I'm going to balance it. Mn is fine. Go and add my waters. Go and add my hydrogens. All right, now add electrons to the more positive side. We need both sides to be a +2. We've got a +2 here, +8, plus a -1, so that's a +7. I'm going to add 5 electrons. Now let's go to the next part. So the next one is ClO3-. Again, the oxygen, you don't leave it off because it's part of a polyatomic. No. Okay, it's part of a polyatomic. So we're going to leave off the sodium because sodium here is +1. It's +1 here. I don't care about it. So then it's going to be ClO4 -1. Now I'm going to balance it. Chlorine is fine. Oxygen is not, though. All right, so now I've got to go back and add my hydrogens. So there's 2. Okay. And then now I'm going to add electrons to the more positive side, so I need to add it to this side, so it becomes 2 electrons here to get it to be -1 on both sides. All right, so now you've got to cancel out your electrons. So both of these need to be multiplied. This one gets multiplied by 2, this one gets multiplied by 5. So the first reaction is 10 electrons plus 16 of these, 2 of these, do the same thing for the bottom. So now you've got 5 waters, you've got 5 of these, 5 of these, 10 H pluses, and 10 electrons. Okay, so anything that's on both sides gets canceled, so electrons go away. Hydrogen, well, we've got 16 here, 10 here, the smaller one goes away, take the difference, so this is going to be 6. Then water, well, this one's a smaller one, so it disappears, this one becomes 3. And everything else is not canceling, so that's part of your net. So your net is 6 H pluses, 2 permanganates, oh wait, 5 chlorates, and then we have 2 MNs, 3 waters, and then 5 of these. Okay, this is the correct answer. Now, there is another way to do this. There's a shortcut. Unfortunately, this reaction, these 2 ions needed to be swapped. Okay, so this is the correct answer, and this is the long way to do it, and this is the way you have to do it if they don't give you a fully balanced equation. Now, if you have a fully balanced equation, what you can do is you can get rid of anything where the oxidation state doesn't change, or technically it doesn't participate in the reaction at all. So let's go through how to do that part. So I'm going to erase all this. Can I do that? Can everyone hear me? Can everyone hear me? Okay, just checking. Okay, I'm gonna erase this. Okay, so the easy thing to do is if you have a fully balanced equation, and I'm gonna just preface this and say this equation is not completely correct. I did accept two different answers. The first one was the absolute correct one. The second one is if you use the trick from when I showed you guys how to do this before. So when you look at this, potassium is +1. Anything that's group 1, you pretty much, unless it's going to be a solid on one side, if it's an ion on both sides, you're going to take it out. This is a -1, this is a -1. Okay, this is a molecule. It stays there. Now, if you have something like hydroxide, or if you have H+ and a redox reaction, you probably need to leave that in, because technically a lot of redox reactions, you have to have an acidic medium. And if you leave the H+ out, what you'll end up seeing is that you're not going to be fully balanced because you've got water on the other side. So when we look at this, we have Mn with an O4 minus, there's 2 of those, so we can have that as 2. Now this is the part where you'll see that it's incorrect, and that's because these 2 ions got swapped here, so it's not really balanced the way it actually needs to be balanced. But I accepted 2 different answers for this one, and on the College Board test, if they give you a fully balanced equation, use it, because you can assume it's completely correct. Somebody, like 10 people would have checked it by then, hopefully. So this is a polyatomic. You leave it as a polyatomic. You don't split polyatomics ever. So you could have written this. Hydrogen we leave in for redox reactions because a lot of them need acidic mediums. This, okay, the chlorine you can leave out, but this, we need that because the oxidation number does change here. And then water, it's a molecule. You can't break it apart. You cannot do that. And then here, this is group 1, chlorine's oxidation number here, it stays the same. This would be the, I'm missing one. And then the chlorate, which should have been 2. Now, if you did it this way, I count it as correct because that would be a correct method if the equation was correct. Yes, okay, so on your exam, you can absolutely do that if they give you a fully balanced, full equation. Yes, you can do that. So polyatomics, you can't separate those. You cannot separate molecules, and if it includes something with an acid or with a base, you're probably going to need to leave the hydroxide or the H+ in, and you'll see that you need to do that because they'll look at the, let me pull that back up. Let me show you. Like if you go to the equation I just wrote, like right here, if I had the H+ and I did not put that in, well, if you go to the other side, you've got hydrogen. So it should be balanced with the atoms as well. So go back and double check to see that you're including everything to make it a balanced equation still. But it should just match up with the ratio that you have in your full equation. You can do this if they give you full equation. And I would advise you do that if they give you a full. If not, the other way is the way you would have to go about it. This is just kind of a trick. So are we good on that particular part? So let's continue on. If you still have a question on the last thing, then you can just type it. So the next one says calculate the mass of sodium chlorate for trial 2 using the volume and molarity of the potassium permanganate and the balanced equation. So trial 2 is what I want you to focus on, okay? And it gives you the molarity in the first one, the milliliters added, and then the mass of the mixture. So essentially what you have is you have a mixture that has sodium chlorate in it and some other stuff. They took that, they dissolved it, and then they titrated it with the potassium permanganate. So if we want to calculate the mass of the sodium chlorate, we need to go from our potassium permanganate, because we have a volume, we have molarity, that's our starting point. You have more information about that, and then you're going to go to grams of the sodium chlorate. So we need our equation for that. And I did also accept 2 answers for this too, based on this reaction and then also based on the net reaction too. All right, so our starting point should be our volume. Never start with molarity, ever. Go to moles of what you have, which is going to be the permanganate. And that's going to be 0.01. Oh, that's liters. So if we have 12 milliliters, we have 0.0012. Here, let's just stir this. We have 0.01 moles over 1 liter. This is going to be for your permanganate. So now go to your sodium chlorate. All right, moles on top of moles, you can use the coefficients. Now, I used both the net and this reaction to calculate this out. So there were 2 correct answers for this because I'm not going to penalize you for typos. Now, moles, and then you got to go to grams. Now, the sodium chlorate weighs 106.5. It's 1 sodium plus 1 chlorine plus 3 oxygen, so you get 106.5 here. Now, when you do this calculation out, you get 0.00625 or 523. The other amount that I accepted was this. So if you got either one of those numbers correct, like if you got either one of those numbers, you got that one great. One of them came from a 5-to-2 ratio, and then the other one came from a 1-to-2 ratio. All right, so the next question, are we good on this though? The next question is asking about the percentage. So this is the total mass of the mixture. So now to get your percentage, you're just going to divide what you got by the total. So if you did this number, it'd be that. And then you have to multiply by 100. Okay, so the thing is, some people put in, they divided it, but they didn't multiply it by 100, but then they put a percentage sign. You don't get the point for that, okay? If you just left it as a decimal without the percentage sign, you would get the point. But you putting the percentage point mark there indicates that you should have multiplied by 100, and you don't really understand the difference. So be careful about that. So if they're asking for percentages, go ahead and multiply it by 100 and add the percentage sign. So this one was 1.03%, and I think this one was about 5. So again, I accepted 2 answers. And also, if for some reason you got one of them wrong, like you didn't do this one correctly, but then you did the next part, you do get a follow-through point for that. So just make sure if you're going to have that percentage sign there, what you need to multiply that by 100. So you have to do one or the other. You can have it as a decimal point, or you can have it as a percentage, but you can't do both. You can't have it both ways. Okay, so I'm going to erase this. Okay, so the next one says, give one possible reason or error in the experimental method as to why the volume in trial 1 is significantly higher than trials 2 or 3. Okay, so when we answer about errors, okay, so here are some answers that I put down. So there's more chlorate in the first sample. So if we have a mixture, and maybe it's not uniform, I think I had a few people actually say, well, the mixture might have been heterogeneous and you took a different sample, so you got a different amount of sodium chlorate. That's completely legitimate. That would be a legitimate response. Overshooting the equivalence point would also be a good response. If there was an air bubble, that would lead to you thinking that you added more potassium permanganate. Those are all legitimate things. I did have somebody say something about Parkinson's. That's not a legitimate thing. No point for that, sorry. I think I had a lot of people say something about evaporation. Okay, so if you had a sample and like you're titrating it, so let's say that you have a beaker, and then you're titrating it, and then the volume of the beaker goes down. However, that doesn't cause this particular error where you are adding more potassium permanganate, because the amount of the moles doesn't change even if you evaporate the water out. So this error, like the evaporation part, would not lead to this particular error. Okay, so I did remember seeing several people put that, but that error is not going to lead to this particular thing. Okay, if you had another response that you just want me to talk about, you can do that. Those are just the main ones that I remember off the top of my head. Okay, so I'm going to move to this part. If there is an answer that you want me to just explain, you can just put it in the chat and I'll come back to it. But let's look at the PES. Okay, so when you're reading a PES and it's asking for the element, make sure you pick the peak that's got the most energy first. You're reading it like an electron configuration, but they can flip this and then the highest number can start here or it can start here. So you just really have to pay attention to where that high number starts. So here's my highest number. That's going to be my peak, or my electrons that are closest to the nucleus. So this will be 1s. So 1s2. The next one would be 2s2. The next one would be 2p6. And remember, you've got a 2, and then you've got a 6 up here. So the height tells you how many electrons you have here. Then we go to the next one, which is 3s. And then we have 3p, and then we have 4s, but be careful because the height here is 1 less than this, so it's 4s1. And if you go look it up on your periodic table, you can say K, and then you could have just given the electron configuration if you wanted, and then that could be your explanation too. All right, so the next one, circle the top of the peak that represents the 2p orbital. Okay, so that would be this one. A lot of you are fine with that. And then on the graph, draw a 3s peak for magnesium. So if you go and you look on your periodic table, you'll see that magnesium has less protons than the potassium, which means it's not able to attract the electrons as much, which means that it will take less energy to remove those electrons. So it should be the same height as, having 2, but it should be somewhere that's to the left, not to the right, to the left of this 3s. So somewhere here. If you'd said anything about it being to the left of this peak, or if it had been over here, that would have been fine. Because you can't really know exactly where it's going to fall. Okay? All you should understand, and all that you need to articulate that you understand, is that this set of electrons will take less energy to remove than the 3s here, because there's more protons. So this one's going to be further down this direction because it takes more energy. They're more attracted. So really, it just needed to be somewhere towards the left of that peak. So you just got to be careful about that. So I see people are writing. Are there any questions about that? It's still going to take less energy to remove than the potassium would. So it's going to be more towards, hold on, let me pull up the PS. So like right here, we've got less energy, we've got more energy here. So when we talk about removing electrons and we're comparing the atom to atom, what we need to do is we need to think about how many protons that atom has versus the other. So it will take less energy to remove those 3s electrons than the potassium. So it's got to be somewhere towards the left. It's going to take less energy to remove them. Does that explain that, or do you still have questions about that, Dylan? If they were asking for 4s, but that's not what the question was asking for. It was asking about 3s. Ah, okay, Dylan, but when we talk about ionization energy, that's the first ionization energy. We're just talking about removing one electron. And here, okay, so if we're looking at the PES spectrum that you have, okay, you're looking at removing, like when we talk about the ionization energy, we're going to remove that first electron from the outermost shell. This is the first electron that would be removed. So yes, magnesium does have a higher ionization energy than potassium. Those are the electrons that it would remove for the first ionization energy, these, which would be higher in energy. So you can't be comparing 4s to these in this particular question. So first ionization energy, we're going to move the first electron from the outermost energy level first. And then this one would be lower for potassium. Okay. All right, so let's look at the next one. The next one's a Lewis structure. For the love of all that is holy, make sure you read the question. A lot of you missed it because you weren't looking at this. It says it obeys the octet rule, so that it should not have an expanded octet. It should also not have an incomplete octet. So we have chlorine in the center. Oxygen, oxygen, oxygen. Okay. Oxygen has 6 valence electrons. Chlorine has 7. Okay. But this is a -1, so you have to add 1. Okay. So that means that you're going to have 26 electrons total. Do that first if you're going to draw a Lewis structure. Okay, so now distribute to the outside. Okay, extra electrons go on the center. Okay, well, chlorine, does it have an octet? 2, 4, 6, 8. Yes, it does. Move away. Now, if you drew double bonds, it might be because you looked it up, and yes, sometimes you'll be depicted with a double bond because of formal charge. But that's not what the question is asking. It's asking you to draw the one that obeys the octet rule. Okay, so that would be the particular answer right there. If you didn't put brackets around it, you weren't counted off though. Technically, yes, brackets would be more proper. All right, the next part is asking about formal charge. So let's look at oxygen. And again, you get follow-through points. So even if your Lewis structure was wrong here, but you calculated it correctly based on your wrong Lewis structure, you got a point for the formal charge. So for oxygen, all of these are equivalent. So what you do is you say, okay, 6 valence electrons minus the number of bonds, which is 1, plus the lone electrons, not pairs, electrons, 2, 4, 6. So it's -1 for all of them. Then chlorine, okay, you've got 7 valence electrons, you've got 1, 2, 3 bonds, 2 lone electrons, not pairs, and then you get +2. So those are your formal charges. Typically on the AP exam, they'll specifically mention formal charge, or they'll say, okay, you have this Lewis structure or this Lewis structure, which one is more probable? If they ask you that, you have to look at formal charge for that. But typically, you don't need to look at formal charge because then you guys start drawing all sorts of weird stuff. Because what you want for formal charge is you want all of them to add up to the charge of the molecule. You also want to give the more negative formal charges to the more electronegative atoms, and you also would like your center to have a formal charge closer to 0. Okay? So, what is the hybridization of chlorine? Oh, I should not erase that. Okay, hybridization, you're going to count the lone pairs and the sigma bonds, not double bonds, don't count because they don't hybridize. So we have 1, 2, 3 bonding pairs, so 3 sigma bonds, and then 1 lone pair. So we need 4 places for the electrons. So we can take 1 place from the S, because there's only 1 orbital in S, and then we need 3 more, so we're going to take 3 from the P, and then we have sp3 hybridization. All right, so the next question, hope you didn't think about this too deeply. It says draw a Lewis structure that would explain why the bond energy in chlorate is actually closer to 322 instead of 198 or 379, which is the double bond. Well, you could have drawn this. You still have a lone pair there, okay? So it's an expanded octet now. So you could have drawn this, or you could have drawn this. You need to have the correct number of electrons though, so you can't have 3 pairs on the oxygen here. And you should still have a lone pair. Should still be 26 altogether. So it could be this, or it could be this, and then the double bonds, of course, could be moved around. What you could not have had is single bonds, because if they were all single bonds, then it would be 198. That would be the answer for the bond energy. If it were all double bonds, oops. Okay. If they were all double bonds, like this, which this would not happen, by the way, then it would be 379. So it can't be this, It can't be this, but it could have been either one of those things, because what ends up happening is it has resonance, so the double bond shifts around. So the bond energy should be somewhere between a 198 and 379. So either one of those would have been accepted. Okay. Okay, another student does a kinetics experiment and collects the data. Determine the rate law. Okay, so what you do, you're just going to compare. I think almost every single person got this right, so that's good. What you're going to do, you're going to compare. So we want to find two experiments where two things stay the same, one thing changes. So let's look at experiments 1 and 3. So 1 and 3. 1 and 3, only the chlorate changes. So we're looking at that one. So if I look, the amount of chlorate changes by a factor of 3. And then if I look at my rate, so what happens to my rate as an effect of changing this? Well, it goes up by a factor of 3 as well. So then X has to be to the first. It's first order. So then we're going to look at experiments 1 and 4. Okay, 1 and 4. HCl changes. Okay, so now since HCl changes here, it goes up by a factor of 2. Okay, and then if I look at 1 and 4, the rate stays the same. So nothing has changed. So X to any power to give me 1, X has to be 0. It's 0 order. It does not get included in the rate law. And then we're going to compare 1 and 2. And 1 and 2, we have permanganate changing. So it goes up by 2.5, which, yeah, you can do that. Makes it difficult to do the lab, but you can do it. And then if I look at my rate, as a result of that, it is also going up by a factor of 2.5. So X is also to the first. So when you write out your rate law, it's rate is equal to K. And then I know a lot of you put R. That's fine for me, but on the exam, just go ahead and write out the additional 3 letters, please. Brackets for the chlorate to the first, and then permanganate also to the first. Okay, so now that's our rate law. The rate value, the constant including the units. So I'm going to erase all this. So you have your rate law now. Just pick any experiment and then plug in the numbers. And then that's going to give you the value of K. So I like the first one because it's all 0.1. So the rate is 3.42 times 10 to the 8th, negative 8. That's equal to little k. That's what we're solving for here. Chlorate is 0.1 to the first. This is 0.1 to the first. We solve for k. We're going to get 3.42 times 10 to the negative 6. Okay, so that's the value of k. Now you have to get the unit for k. It's second order. So if I was going to do this, my unit for rate, okay, is meters per second. K is unknown. I don't know what the unit is right now unless you memorize it. Well, molarity is M. Molarity is M. So what do I need to put here to get to this point? Well, I need to get rid of an M, so it needs to go on the bottom. And I need an S. So that's my unit. All right, do we have any other questions about this particular question? I'm going to stop. Ugh, bothers me. Are we good with Q1? Do you see which ones you missed? Now, if you submitted Q1 late, I have it, I just haven't graded them yet. But you should, if you have your work in front of you, you should have an idea of where you're going to get, or what you're going to get for the points. Okay. So a couple of things that were shared with me last night. So next week, I'm going to go into AP Classroom so you guys can do like a practice run. I'll pick maybe one or two of their FRQs. I'll just tell you this, like, AP Classroom does not impress me very much. That's why I've never used it throughout the year. We will do a practice run with it because you need to practice uploading. Okay, the things that were shared with me last night. Let's see. Okay, first of all, do not use Internet Explorer. I think that's kind of well known. Don't use Internet Explorer. They said Google Chrome is the best. They also said they're not going to expect you to draw anything, so I don't expect Lewis structures. I don't expect particle diagrams or any of that. You can have a Google Doc open with you. You can also have like a Word document open. So if you want to copy and paste your answer into their format, you can do that. Now you can also take pictures and upload it that way. So if you want to, because we're going to have calculations. I don't know the extent of the calculations they're going to have, but they did say that we're going to have some. So if you want to have paper out and then upload it as a PDF or a picture, you can do that. If you choose to use paper, you need to make sure that you put your AP ID on the top, the page number, so how many pages do you have? Make sure you number that and your initials. Do not use a pencil, just for the sake of the fact that if you're doing this, you want to make sure it's dark as possible. The most important thing that they emphasized over and over and over again is, first of all, if you run out of time, sorry about your luck. That's kind of what was told. So you need to make sure that you're watching the time, and then for the love of all that is holy, if you're about to run out of time, you need to make sure you submit your work. Now, once you hit submit, that's it. So if you hit submit before you've actually put all your work in, that's it. They're only going to grade what they get. Okay, so they kept saying that over and over and over again. Also, they're going to email you an e-ticket. The e-ticket's going to be important. You're going to want to print that out so that you have that information. Okay. So basically, once you hit submit, even if there's like an issue, they said that they have it so that the system is going to upload it no matter what. It just may take some time before it actually uploads. So putting your work in and hitting submit is the most important part. I am going to go in the next couple of days, because apparently it's live now. It wasn't supposed to be live until May 4th, but it's live now. I'm going to go in and kind of play with it and see, so there should be a way for me to get in there and look at what you're looking at. And I might try to do like a video on how to troubleshoot that. And I'm going to upload more information. But that was some of the most important information that I learned last night. So next week we're going to practice. It will be a grade. I'm going to make it worth more points because it's going to be practice uploading, which I think is extremely important. And then also I'm going to give you another FRQ, which is also important. Okay? Any questions about that right now? I will have more information coming, but those were just some of the most important things that I picked up last night. What score? Okay, so Sarah, are you talking about how they're going to assign you a score? What the curve? And I'm using quotations because they're we don't curve the exam, and I'm yes, you do. So if you're talking about that, is that what you mean? Okay. In past years, you need about 75, but I think last year you needed closer to an 80% to get a 5. And I think you needed about a 52 last year to get a 3. The 4, I don't remember what the cutoff was for that. However, this is all new. I've never seen them do it with only, I think it's only essentially gonna be 20 points. So how they do that, I don't know. So honestly, I can't tell you one way or another. I'm just gonna say, like, do all the practice that I give you. That's what, from what I understand, because it's 2 long FRQs. Now, could I be potentially wrong on that? Possibly. Don't quote me. I will go back and double check on that. So yeah, I'm gonna say you're probably gonna want to aim for at least 10 to 12 points. But like I said, I don't know. This is all unknown to everybody. So what I'm going to say is, like, do all the practice problems I give you. Make sure you understand all of it. Do more practice problems. So, like, go and get 2019's FRQs with the scoring guidelines. You can find all that online, and do as much practice as you can. Okay. And I will say this, like, they've said, oh yes, they can use Google. Yes, they can use their notes. Yes. I'm going to tell you this, you're going to waste so much time doing that. You're better just going in and just writing and doing as much as you can, do as much as you know, and then you'll probably fare a lot better, because they're not going to ask you questions that you can just simply go look up. They're going to ask you application questions. So don't fall for the trick. Don't waste your time. At this point, practice as much as possible. Now, on Friday, I'm going to try to pick, like, I think a lot of people said equilibrium or help with FRQs. So what I'm going to do, I'm going to go look for a particular type of equilibrium problem that I think that they could include, and go over that as an FRQ. And then I'm going to kind of, like, look at some other things for equilibrium. I'm going to go back and double check your poll, and then we're going to do something like that on Friday. All right. Does anybody have any other specific questions? If not, I'm going to let you go. All right, guys. I'm going to let you go. Have a good day. If you need anything, please, please, please just send me a text or shoot me an email, okay? No problem. You too. All right, guys, have a good day.